In this presentation, I'm going to go through three basic types of nuclear radiation, as well as show how to write radiation reactions for those types. So let's start with a simple type, which is alpha radiation. In alpha radiation, the nucleus of our unstable isotope is going to release an alpha particle. And what an alpha particle is it's two protons and two neutrons stuck together. So it will have an atomic number of 2 and a mass of 4. And in some cases, because this corresponds to a helium nucleus, we can actually say that an alpha particle is very similar to a helium atom, and you'll sometimes see that represented as such. And what is happening in this radiation is our original isotope will create both an alpha particle, two protons and two neutrons, plus a daughter particle, which is basically what we started with, minus two protons and two neutrons. And this is also called alpha decay because this original parent isotope is decaying into these two parts. So let's see how we write a radiation reaction for alpha decay. First, we'll write the nuclear notation of the element or isotope, and we will omit charge for now. In this case, for this example, I'll start with plutonium-239, the mass 239 at the top, and the atomic number 94 at the bottom. Next, I'll draw an arrow to show the products of my nuclear radiation. So this is like saying that plutonium-239 is becoming something new. That's really what our arrow represents. And finally, we'll write out the nuclear particle which was emitted, in this case, an alpha particle, and whatever that resulting atom is. So we start with plutonium-239. We write the arrow to show that it's becoming both an alpha particle and uranium-235. So how did I get here? Well, if I started at a mass of 239 with my plutonium, and I took away 4 mass in the alpha particle, I should be left with 235 as my mass. The atomic number, we start with 94. I'm losing 2 of that to the alpha particle, and I'm ending up with an atomic number of 92, which tells me my element will be uranium, which has an atomic number always of 92. All right, let's look at one example step by step. In this example, we'll start with polonium-210. Polonium has an atomic number of 84. We're first going to write the arrow to show that the polonium is becoming something new. And since we know it's alpha decay, we can show that we know it's becoming an alpha particle along with something else. So we know it has to become an alpha particle with a mass of 4 and an atomic number of 2. We'll write this plus sign to say that something else is being created. And if we do our math, we're going from 210, losing 4 to get a final mass of 206. And we're losing 2 protons to go from an atomic number of 84 down by 2 to an atomic number of 82, which tells us that our final element is lead, or Pb. Now, real quick, if we look at this through a math lens, it's kind of like we're saying that polonium we started with is equal to the 2 pieces on the right. And that effectively is true. The polonium becomes these 2 pieces. We don't lose anything else. It's simply these 2 pieces really separated. If we put them back together, we would get back to what we started with. The reason in chemistry why we use this arrow instead of an equals is because we're suggesting that what we started with is becoming something new. It's sort of a one-way street, whereas an equal sign suggests that both sides are the exact same thing or equivalent. In this second example, we're going to start with thorium-234, which has an atomic number of 90. If you'd like, you can pause the video here and test yourself on how to write an alpha decay radiation reaction. But we'll proceed here. First, we'll write our arrow to say that thorium is becoming something new. We know it's losing an alpha particle. We write the plus to show that something else is being created. And we should end with radium with a mass of 230 and an atomic number of 88. That's really how we write alpha decay radiation reactions. Let's move on to our second and third types of radiation. This is going to be beta radiation, and we're going to separate that out into 2 types. The first is called beta minus decay, and this is where a neutron changes into a proton, effectively releasing an electron and something called an antineutrino, which we won't quite get into. Effectively, our mass won't change because we assume that protons and neutrons have pretty much the same mass, but our charge will change because we're gaining a proton. We're changing that neutron into a proton. Contrast that with something called positron emission, which can also be called beta plus decay. And this is where a proton changes into a neutron and it releases something called a positron. So these two types of radiation, beta minus decay and positron emission or beta plus decay, they're kind of like two sides of the same coin. Beta minus changes a neutron into a proton, and beta plus or positron changes a proton into a neutron. Let's take a look at how to write these reactions. We'll start with beta minus decay. And in this case, our example starts with carbon 14. We'll draw our arrow, and in this case, we'll draw our beta particle. Notice that we're saying that the beta particle has no mass because remember, we're not losing mass with the beta particle. And it also has a charge of -1. So why did we use this -1? Well, we know that our proton count is decreasing. So it's like saying that our beta particle has a negative charge. We then say a plus symbol to say that we're adding, and we'd end up with nitrogen with an atomic number of 7 and a mass of 14. Notice that our mass did not change with beta radiation or beta minus decay, but our proton count went from 6 to 7 because we gained a proton. So it's like saying 6 minus the -1 in the beta particle equals 7 in our final particle. And if we were to add the right side up, as that plus symbol suggests, you'll see we'll get back to what we started with. Here's an example that's a little less handholdy. If you want to pause the video here and test yourself on it, feel free. We're going to start with potassium 40, which has an atomic number of 19. As with all examples, I'll start off with the arrow to say that it's becoming something new. I'll write my beta minus particle, the plus symbol to show that something else is here, and then an atom with the same mass but one more proton, because that's what beta minus decay is. And an atomic number of 20 does give us Ca or calcium. Notice that the math still works out. 19 minus -1 does indeed give us 20. Now let's take a look at beta plus decay. Beta plus decay, again, you can pause your video if you want to test yourself, even though we haven't shown the beta plus particle. In this case, we'll start with potassium again, that K. We'll use a slightly different mass number though, 38. As always, we'll write our arrow, followed by our beta plus particle. Notice in this case that we are losing a proton, so our beta plus particle, it's kind of like it's worth one proton, but we know the mass doesn't change, so the beta particle still has no mass. And we have to write whatever our final product is. So we use that plus symbol, and you'll see we end up with argon. Notice again, the mass did not change. 38 minus 0 gives us 38, but our atomic number did. 19 minus 1 gives us 18. And this should make sense, because in beta plus decay, or positron emission, we are effectively changing a proton into a neutron, so we would expect our proton count to go down. All right, I hope this video helps you understand nuclear radiation reactions and how to write them a little bit better.